Hello, my name is Dan Cook and today I'll be presenting my research on the thermal impacts of apiculture on the bee colony. So I'm a PhD candidate at Queensland University of Technology, due to finish in the next couple of weeks, and I'm conducting transdisciplinary research between apiology and industrial design, which is the design of products and how people use things. And what I'm looking to do is address the gap between apiology and apiculture. As well as this, I'm not just a theoretical beekeeper, I also manage the QUT research apiary, which is currently around 50 hives, but we're expanding up to 100 in the next couple of months. I'll get rid of my ugly mug and then we can get on with it. Now, this research is partly funded by Hort Innovation and the Australian government, as well as QUT and Plant Food Research. This presentation is a summary of recent research, and we've released this in a Journal of Economic Entomology in a paper entitled Thermal Impacts of Apicultural Practice and Products on the Honeybee Colony. And if you fancy some light bedtime reading or having trouble getting to sleep, then the link is down the bottom for you. Now, as an industrial designer, I wanted to look at the entire practice of beekeeping from basically the kind of bee and cell level all the way up to the truck level. And to this end, I asked two main questions, which was how does migratory apiculture impact bee colonies, and what are the processes and pain points in migratory apiculture? Now, we found several. My entire study looked at these kind of 5 main areas, all affecting colony health, which were hive design, the practice of beekeeping, transport, pollination services and audits. But today we'll be looking at 2 of these things, which are hive design and practice and their impacts on temperature. So why does colony temperature matter? Well, chilling the brood causes bee retardation and it damages cognitive functions, mainly affecting their memory. And what this means is that the bees can't find their way back home, or they can't learn their location from the hive, so basically they don't come home. Now, colonies require heating, and if the bees are doing heating, then they are out getting less nectar and doing less pollination. And you're also introducing a measure of stress. Now, I'd like to define the word stress here. Stress occurs when animals have to make prolonged physiological and behavioural adjustments in order to cope with their environment. Now, this is an important definition because we'll see that creating increased heating activity in a bee colony is a form of stress. So how do the bees heat the hive? Well, a bee can generate temperatures up to around 43 degrees Celsius, and they do this by flexing their antagonistic wing muscle pairs. And now this came about evolutionarily through pre-flight preparation. By being able to warm themselves up on cold days, they gain a competitive advantage to get to that nectar or pollen before other insects who can't heat themselves up do. Now, one of the fascinating things here is that heater bees can be aged from 3 to 27 days old after they emerge from the capped cell. This is interesting because a lot of this period actually overlaps with many other jobs, and importantly it overlaps with foraging for water, propolis, nectar and pollen, and they can jump back into this role when they're needed. Now, there are 2 main methods of heating up brood. The first one is a thorax pressing, where the bees do a little push-up on top of the cells, heat themselves up, and they transfer the heat straight through to the cell underneath and the cells around. However, this is not as efficient as the in-cell heating methods that they use. And this is where they will crawl into a cell within the brood comb, and in this brood comb there's normally about 5 to 10% of the cells left empty in healthy comb, obviously more if you've got problems or a poor queen or disease. And they'll crawl in and they'll basically heat themselves up, transferring their heat energy to all the cells around them, but also the cells on the opposite side of the foundation. Now, you can see this by looking for their abdomens pumping in and out when they're within the brood nest cells. Now, this was previously thought to be a resting behaviour or a cleaning behaviour, but has since been shown through thermal camera images like the one on the right just to be actually heating. And they can do this activity for up to 30 minutes, pretty much continuously. Now, Heat generation takes a lot of energy. In fact, to give you some numbers, it takes about 65 millijoules per second, which is about 3.9 joules a minute. And that produces a thorax that is about 40 degrees Celsius. Now, to put this in context, a milligram of honey contains 12 joules, which is enough to lift half a kilo or 1 pound up to about 7 feet, or just over about 2 meters. And 1 gram of honey is equal to about 12 kilojoules, which is equivalent to about 3 food calories or kilocalories. And the adult human needs about 8,700 kilojoules per day, or 2,200 calories. Now, when we talk about energy in time, we talk about watts, and 1 joule per second is a watt. So, to put this again in context, we can talk about how the beehive and maintain the brood nest temperature uses about the same amount of energy as running a 20-watt light bulb continuously. And this is in normal conditions, not in a harsh winter cluster or in a summer condition. So I wanted to ask a couple of questions, having defined the parameters of temperature. The first was, what happens to a beehive when we put a cool or a cold super on top? Well, a number of things. First, the heat rises up from the brood nest, and this heat will start heating up the cooler frames and comb or foundation. And the colony beneath now has a heat deficit. And they can't basically move up to take advantage of this because above them is cold, there's no stores, there's no brood, and normally there's a queen excluder preventing the whole colony moving up. Basically, this deficit means that they need to start doing some increased heating activity to help maintain that brood nest at around 35 degrees Celsius. Now, I wanted to know how much energy that took. So I did some theoretical calculations and we created a mathematical model. And basically what we showed was that heating up foundation, either plastic or wax, there's not much difference between the two, takes around 150 kilojoules to take a super stored at 15 degrees Celsius up to this optimal temperature of 35 degrees. Now, a sticky or extracted comb will take double this at 350 kilojoules. And if you're unlucky enough to try and actually throw on a full super of honey, which hopefully no one's actually doing, or you're just wondering how much energy is contained within a full depth 10 frame super of honey, it's about 1.3 megajoules of energy, which is a vast amount. Now, one of the questions you might have in your minds at this moment is, if it takes more than twice the amount of energy to heat up stickies as it does to heat up foundation, should I always be putting foundation in? And the answer to this is a resounding no. That's because the energy required to build out the wax foundation to proper comb structure is around 382 megajoules of energy. It's absolutely huge. And basically that's 283 times more energy than it would need to heat up those stickies. Now again, I like to put these things in a context. So that 382 megajoules of energy to build that comb is the equivalent to 65 Domino's Meat Lovers pizzas. So that's a lot of pizza, and that's a lot of energy. But I was still looking for a better way to express these numbers. So I came up with a new unit, which we're going to call beam minutes. And a bee minute is basically the number of minutes it takes a bee to do heating work. So we can see here that foundation, whether it's wax or plastic, takes around 35,000 minutes of bee activity to take it from 15 degrees Celsius to 35. An extracted comb, or stickies, take around 80,000 bee minutes. So 80 bees for 1,000 minutes, or 1,000 bees 80 minutes. And it's a lot of work. Now if we want to put that into a real world application, now our real world application is this graph here. This is Brisbane mean monthly highs and lows. So the warm coloured bars are the monthly high temperatures, and the blue coloured bars are the monthly low temperatures. And this is all daytime. If we then plot the energy required to heat up a super from 15 degrees on each of these days, as shown as the blue line for the cold days and the red line for the warm days, you can see there is quite a difference in the amount of energy required to heat up that super. In fact, it's 3 times more energy. Right? So that could be a lot of foragers out collecting you some nectar, making you some more honey, or going out to do a pollination job. Now, not everywhere in the world looks like Brisbane. So to give you an example of another place I recently did, if we compare this to the San Francisco Bay Area, we get this. This curve basically shows that the difference between a cold day and a warm day in San Francisco out at Alameda is around 30,000 extra bee minutes. And this is basically pretty typical of most temperate regions, so this is why this is a good example. Now, having quantified the heat energy that's in a super and how much energy it takes to warm those supers up, I wanted to know how much heat energy is actually stored within the honey that we take away. And I asked 2 questions, which was, does honey help stabilise hive temperature, and does robbing this honey actually impact the bee colony? So I set up a series of experiments using supers full of either full honeycomb or stickies, and we put them in a special temperature controlled oven. This oven was set to spend 12 hours at 35 degrees Celsius and then 12 hours at 15 degrees Celsius. What you can see is that this blue line is the ambient temperature of the oven. And you can see it basically sits quite nicely at those 2 temperatures and then drops or rises very sharply. Now this yellow line is the stickies, or the extracted comb. And you can see what's happening here is that they are following the ambient temperature very closely. They take a little bit of time to cool all the way down or warm all the way back up again, but it's pretty similar. So we're looking at only an hour or so to actually get that temperature drop. However, when we look at the filled comb, we see that there's not much temperature variation at all. In fact, it's only around 6 degrees Celsius. And what's happening here is the honey is absorbing excess heat energy and then releasing it out when it gets cold again. So to answer the question, does honey help stabilise hive temperature? The answer is a resounding yes. And we can see that quite clearly because the honey acts as a thermal mass. In fact, the temperature rate of change is just 4% of the ambient temperature change. So we can say that the honey provides a measure of thermal hysteresis, which is a resistance to change. It absorbs the excess heat and it releases that heat back out into the hive when there's a temperature drop. So, does robbing honey impact the hive? The answer is yes, very likely. More temperature variation means that there needs to be more heating activity in the cold, more fanning activity in the hot weather, and it means your workers are managing temperature and they're not foraging. So next up, I wanted to know what the impact of the actual hive itself was. Now, this is the Reverend Lorenzo Lorraine Langstroth, the inventor of the hive, arguably the inventor because there are other people who did a lot of work towards it, such as Huber, Zerzon and Propokovich. And basically, all of their work accumulated in this gentleman here, Langstroth, bringing to market a commercially viable movable frame top opening hive. You can actually see the work of the others still in Europe in the AZ hives, which arguably are actually a better system for the bees, although not as commercially viable. Now, I'd like to put the hive into context. This was in 1870, and you can see that the boxes in the background and in the foreground and the frame and the wax foundation are all very, very familiar because they haven't really changed. In fact, Langstroth is holding there a Hoffman frame with the self-spacing frames, and that's a printed sheet of wax foundation. So this was kind of the height of technology at the 1870s. So, to sum up, 1870s, state of the art is a wooden box with wooden frames with a bit of wax in it. Now let's compare this to the dairy industry. In 1870, the dairy industry's state-of-the-art technology was a metal bucket and a stool. If you were lucky, you had a young lad, like the guy in the centre of the picture here, who would run buckets backwards and forwards to the shed where they poured it into the churns. If we jump forward to recent years, what we see is that the dairy industry has progressed a long way. Cows are now RFID tagged and identified as they come into feed. While they feed, they are milked. How much milk they produce is automatically recorded. Robotic milking machines analyse the milk as it's going through. There's some separation and homogenization, and it's basically tracked all the way to supermarket shelves. We know exactly how much the cows eat. Now, comparing this back to beekeeping, and apart from the fact that we've got trucks and something to move boxes with, we're still a wooden box containing wooden frames, right, with a bit of wax in them. Now, this is where I tend to get a lot of kickback from beekeepers, because lots of people say, well, if it ain't broke, don't fix it. And my favourite answer to this is, I quote Henry Ford, who invented the motor car. And he said, if I had asked people what they wanted, they would have said faster horses. And in our case, we have a product that has been doing really well for an awful long time. And we haven't changed it because we've always been producing honey and it's a great system for that. But it was invented 160 years ago for honey production. And today we do a bit of honey production, but pollination services globally is worth over 100 times more. In fact, it's worth about $240 billion per annum, compared to about a $2.34 billion global honey industry. And Australia has a pollination industry that's worth about 14 billion, with a B, billion dollars. So this comes to that big question, is why are we still using a 160-year-old honey collection system for pollination? So to find out the impact this was having on our bees, I asked another set of questions and did some more experiments. I wanted to know what the thermal properties of the Langstroth Hive were. I wanted to know, how does the hive contribute to heat loss? So I created mathematical models of a hive made from various materials using identical dimensions, just as a kind of a theoretical experiment to show what we could do by changing up our materials and using something with modern material research and design. I set the inside of these hives at the ideal 35 degrees Celsius, and I compared it to external temperatures that varied. Now I know there are going to be some people here who say, well, not every hive is 35 degrees Celsius all the way through. And to them I reply, yes, I know, but doing it any other way, the maths becomes really hard, and I'm not that good at maths. So here are the results. What we found is that a wooden hive uses a vast amount of energy, and you can see that here in this green line. So if you look at the solid lines, these are the hives as a whole. And we see up here at the top, wood uses about 100 watts of energy. And it loses 100 watts of energy at 15 degrees Celsius out of its sides and lid. Whereas something like expanded polystyrene loses a quarter of that at about 23 watts. Now, really interestingly, if we look at the two dashed green lines for wood, we see that both the lid and the walls lose about the same amount of energy. So they're both sat around that 40 to 45 watts of heat loss mark. So beekeepers often ask me what I would do to solve these problems that I'm pointing out. And I say, if I could improve one thing on the Langstroth right now, it'd be lid insulation. It's an easy fix. You can pop down to your local hardware store and there's a myriad of options such as foam or earth wool insulation or any form of the packing foams that we get, which are waste products at the moment. And it's very easy to modify the thick migratory lids into slightly thinner lids but with a big layer of insulation, or place foam on top. Because better lids means you get less energy loss. In fact, you'll halve the energy loss almost, right? And if you've halved the energy loss, that means you've got less colony stress. Less colony stress means that you've got healthier, happier bees. Now these healthier, happier bees are going to be going out and doing more work. They'll forage more nectar, they'll forage more pollen, right? Which is good for you because you get a better return. So how does this all apply to you? Well, to answer this, I'd like to ask some questions. Now there's normally some fairly energetic and active debate at this point, but this is my kind of takeaway. Why do you do what you do? Is it because it's what you've always done? Is it because it's how you were taught to do it? Right? And does this new information shed any light on the practices you do? Right? And what small changes can you make to reduce bee thermal stress, to make happier, healthier bees? For example, are you still going to super on a cool day? Or are you going to put your supers underneath a black tarp and let the sun warm them up a bit, saving your bees tens of thousands of minutes and getting you more nectar in the hive so that you can have a better honey return at the end? Right. So, I'd like to thank you all very much for your time. Please feel free to contact me through the total, and I hope you all have a lovely day. Thank you very much.